In section 6.6, we're going to look at graphs of transformed sine and cosine functions. So our objective is to graph transformations of the sine of x and cosine of x function. Those look like y equals a times sine of x, sine of bx minus c plus d, and y equals a times cosine of bx minus c plus d. We're going to talk about the transformations and the effects of those values. We'll use those to determine the amplitude, period, and phase shift of the graph. And then as a separate topic, we're going to look at the graphs of some sum functions. The third objective right here is in the book, but we're not covering this one in the content of this course. It's about dampened oscillation functions. So we're going to look at the first two objectives from this section. Quick review here on transformations of graphs in general. For the function f of x, we're going to write out the transformations in function notation. So first here, this function needs to be shifted up 3 units and shifted to the right 2 units. So I know that a shift up is going to affect y, and therefore it's going to happen outside of the function. And a shift to the right is going to affect x, and so that's going to happen inside the function. So I'm going to have f of a right 2 shift inside the function is going to be an x minus 2 shift. Happening inside the function is going to be a shift left or right. And then shifting up 3 units will be adding 3 to the outside of the function so that we affect the y variable. So f of x minus 2 plus 3 shifts 2 units to the right and up 3 units. Let's look at this again. With the next transformation, we are going to be shifting to the left by 1 unit. We are going to be reflecting over the x-axis. And we're going to be vertically stretching by a factor of 3. So there's 3 transformations here. The left 1 shift affects the x. Left and right is the x value, so that's going to be inside the function. Reflecting over the x-axis, it's going to take top to bottom, so that is a y shift, so that's going to be outside the function. And vertically stretched, it's going to affect y, so that's also going to happen outside the function. Anything that affects x happens inside, anything that affects the y happens outside. So we're going to have our function f, and inside the function, we're going to shift to the left. That's going to be an x plus 1 to go left. To the right was minus. To the left is plus. Inside operations are also opposite of intuition, right? So a right would be a positive, but we use the opposite subtraction for the right. Left, you might think negative, but we're going to use the addition for inside the function. And then the y flip, that's going to be a multiply by a negative 1, and a vertical stretch is going to be a multiply by 3. So we're going to multiply by negative 3. The negative portion right here is for the reflection, and then the 3 portion is for the vertical stretch. All right, continuing on the next one. Here, we need to stretch horizontally by a factor of 2. We need to shift down by 3 units, and we need to shift left by 2 units. So stretching horizontally, that's going to be affecting x. That needs to happen inside the function. Shifting down needs to affect y, so that's going to happen outside the function. And shifting left is going to, again, affect x. That's going to be inside the function. Okay, so if I start my function, f of, when we did our vertical stretch, that was a multiplier of 3. A vertical shrink would have been a multiplier of 1/3. When I want to stretch horizontally, remember inside operations are opposite intuition. So instead of a multiplier of 2, a multiplier of 2 would be a shrink horizontally. To stretch horizontally, I'm going to need a multiplier of 1/2 times the quantity. We have x, and we're shifting to the left 2. That's going to be x plus 2. I'm going to need that extra set of parentheses in there to make sure that my horizontal stretch factor affects the entire inside, including that left shift. So let's go like this. And then finally, on the outside, we're going to go down 3. So outside the function, we'll subtract 3. That's our outside shift. Okay. Now, part D says, if we found out that the function f of x is actually the function f of x equals the sine of x, how would this new sine function appear after the transformations in part C? So same transformations here on the sine of x function. So my new function, g of x, is going to take f of x, and it's going to stretch it horizontally by a factor of 2, shift it down 3, and left 2. So instead of f of x, we're going to use the sine function. We're going to have our 1/2 for our horizontal stretch factor times the quantity x plus 2 to shift it to the left 2, and then we're going to shift it down 3. Now that we know what function we're using, that sine of x function, let's go ahead and graph so we can see what these transformations do to the graph. All right, so we've got a decimal graph here. I want to make sure that I'm in radians. I should always graph these functions in radian measure, so it's in radians. I'm going to graph the original parent function, f of x equals sine of x. Let's do a little rescaling on this because we know that the maximum height for the sine x function is -1 to 1. So let me change the step right here to be by 1. And then the steps on the x-axis need to be in terms of pi. So let's do a pi halves indicator right here. And just zoom this out a little bit. There we can see pi halves, pi, so on, so that we can see our graph properly graphed in terms of good numbers for input and output. All right, so let's look at one transformation at a time. So we're going to take our sine function, and let's do first the horizontal stretch. So we'll do the 1/2 multiplier. So we should be able to see that this graph has been stretched horizontally by a factor of 2, making it twice the width. So this point right here at pi halves 1 has been stretched over to pi 1. That's twice as far away, right? Pi halves times 2 would be at pi. And similarly, this point right here stretched over to this point right here. So the blue graph looks twice as wide as the original. Now, I'm going to keep that change right here, that 1/2 x, and so I can see the next transformation. The next transformation should be shifting this graph to the left 2. So we're going to put that plus 2 in here, and now we can see that my point got moved to the left by 2 units. It's no longer at a whole number multiple of pi right here because 2 is not a pi of multiple, but if this was at pi, this number right here should be whatever pi minus 2 is. So 1.14 or whatever that is, right? So I've shifted 2 units in the direction that is to the left. Looks like we've done that. Okay, so let's update our function so we can see the last transformation. We're going to take this function and we're going to pull it down 3. So the final graph right here will be the same graph now pulled down by 3 units. And looks like that's what we got right here. So the original function, sine of x, has all 3 of those things happening to it. Horizontally stretched out by a factor of 2, shoved to the left by 2 units, and then pulled down 3. All right, so all of those were accomplished by those 3 transformations. In order to make a sketch of this by hand, I did use decimals to confirm that I've done the transformations correctly, but if I were to want to graph this and draw it properly by hand, I'm going to need to recall what the graphs of y equals sine of x and y equals cosine of x look like. So let's take a look at the base functions, the parent functions for y equals sine and y equals cosine. The sine of x graph starts at 0, 0. And then by pi halves, it's reached a height of 1. Then by pi, it's gone back to 0. And by 3 pi halves, it's reached a height of -1. and then it's gone back to 0 at 2 pi. So if I draw just the left side or the right side of this graph, that's one period of the sine of x function. I can continue this graph on the other side at negative pi halves. By symmetry, I'd be down here at negative 1, back to 0 at negative pi, back to 1 at the negative 3 pi halves, and then back to 0 at 2 pi. So let's draw in the other side of the wave function. Okay, so this is the graph for y equals sine of x. And then let's draw our graph here for y equals cosine of x. Cosine of x starts at 0, 1. So it's going to start up here at the top. It's going to come down to 0 at pi halves. Then it's going to be at negative 1 by pi, back to 0 at 3 pi halves, and back up to 1 at 2 pi. So that's the right side. Let's go ahead and continue on the left. If we're starting at 1, we're going to go to 0, to negative 1, back to 0, and then back to positive 1. So my scale on the x-axis is by pi halves because that is the amount of space it takes to go from a 0 to a 1. So I can always just mark off where the 1s, the 0s, the negative 1s are on equal intervals of pi halves, pi, 3 pi halves, and so on. Because again, on the unit circle, those measurements, 0, pi halves, pi, 3 pi halves, etc., those are the axes. And so on the axes, the coordinates for both x and y, for the sine graph and the cosine graph, are either 0 or 1. So that's why we use those as a convenient scale across the x-axis for both graphs. Okay, so these are the two parent functions. We want to have a picture of our two parent functions in our head anytime we're going to do transformations of those graphs. Okay, so topic 1, variation on basic graphs. We do know what all 6 basic trigonometric functions look like, so we just drew for ourselves the y equals sine of x graph. So this is just another look at that graph. We know that its domain is all real numbers, its range is negative 1 to 1, and its period is 2 pi. We just also drew for ourselves a graph of y equals cosine of x. So this is the cosine of x function. Its domain is also all real numbers, its range is also negative 1 to 1, its period is also 2 pi. In one of the previous sections, we did examine the graphs of tangent, cotangent, secant, and cosecant. So the tangent graph, we remember, looks like this. It's got asymptotes at all multiples of, odd multiples of pi halves. This is a different way of stating this. When we had stated the domain before, I believe I used the notation that x was not equal to 2k plus 1 times pi halves. That's all odd multiples of pi halves. Notice that in the notation that they've given here, they've just distributed the pi halves. So 2k times pi halves, that would be 2k pi over 2. The 2's would reduce. That would be k times pi. They did use the letter n instead of k, but that's where this piece comes from. Then the 1 times pi halves is pi halves. So they've used the same thing, but distribute it and use the letter n instead of k to list the domains. Just wanted to share that how that overlaps with what we saw in the last section. A range, we said in the last section, was going to be negative infinity to infinity, and the period was going to be pi. All right, then I'm going to drop down to cotangent because that is the reciprocal of tangent. So we just did tangent. Let's look at cotangent. So the cotangent function looks like this, and its domain is all x's that are not integer multiples of pi, so all x that are not k pi or n pi. Its range is also negative infinity to infinity, and similarly, its period is also pi. Sine graph, let's look at the cosecant graph. since that is the reciprocal of the sine graph. We know that we've got these U-type shapes and we've got asymptotes. These asymptotes here are going to be at all multiples of pi, all integer multiples of pi. And the range, saw in the last section as well, we get negative infinity up to -1, then we stop and we go from +1 up to positive infinity, and that period is 2 pi. For the secant graph, that's the reciprocal of cosine. So we can see our U shapes over here. We can see that our asymptotes are once again at the pi halves, 3 pi halves, and so on. So our asymptotes are also at those odd multiples of pi halves. So we can distribute that if desired, or if not, we could write that as x naught equals 2k plus 1 for the odds times our pi halves, same thing that we had for tangent. Two different ways, just one is distributed, one is not, of expressing the domain. Our range here, very similar to the range for cosecant, is going to be negative infinity up to -1, and then 1 up to infinity. And this one has a period of 2 pi as well. Okay, so we are mainly going to focus on the graphs of the sine and cosine functions. We want to know what their parent functions look like without having to refer back to a graph. But for the parent functions of the tangent, cosecant, secant, and cotangent, it would be okay to be able to refer back to a graph for these if you needed to look up what the parent functions looked like for one of the other 4, not the primary 2. Okay, so we know what the parent functions look like, and we're going to apply some transformations just like we've done with other functions in the past. In this function, y equals 2 sine of x plus 3, we want to ask what the base function is. The base function would be y equals sine of x, and then what the transformations are. So one of the transformations is going to be the multiplier of 2, and one of the transformations is going to be this adder of 3. Those are both outside the function. They're not in parentheses with x. So that means that the 2 is going to be a vertical stretch by a factor of 2. And the 3 is going to be a shift up by 3 units. All right, so the original y-intercept for the sine function would have been at 0, 0. If I stretch that by a factor of 2, 2 times 0 is still 0. That stretch wouldn't change where the y-intercept is, but the shift up 3 is going to change it. So the new y-intercept is going to be at 0, 3. Okay, so that's going to be from our up 3. Now for the domain and range. So the domain, it was all real numbers to begin with, so it's going to stay as all real numbers. For the range, it did go only down to -1 and up to +1, but when I stretched this by a factor of 2, that would have pulled it up to 2 and -2, and then I'm going to push it up 3. So let me make a note about range over here. We had -1 to 1, and then we stretched. So it became -2 to 2, and then we went up 3. So -2 plus 3 would be 1, and 2 plus 3 would be 5. So that's why the range on this one is going to be 1 to 5. Okay, let's look at the next one. Transformations. So I've got a negative multiplier. I've got a 1/2 multiplier, both on the outside. And then I've got a 4 multiplier on the inside. The base function for this graph is y equals cosine of x. The transformations on the outside, we've got that negative multiplier. That's going to be a reflection across the x-axis. It's outside, so it's a y shift. So we're reflecting across the x-axis to change y's from positives to negatives. And then we have a vertical. It's a 1/2, so it's a shrink by a factor of 2. So it is a 1/2. The shrink factor is 2. I don't need to say 1/2. That would be redundant. It's a vertical factor, vertical shrink by a factor of 2. And then the 4, that's going to be a horizontal stretch or shrink. Horizontal stretches are fractions less than 1. So horizontal shrink is going to be that number, 4. It's going to be a horizontal shrink by a factor of 4. All right, so the location of the new y-intercept. So the y-intercept on the cosine function normally is at 0, 1. This is going to be reflected down to 0, -1 and shrunk up to a half. So the y adjustments here are going to make this 0, -1/2. There's not going to be any effect based on horizontal shrink because 1/4 of 0 is still 0. But both of these y factors are going to affect the y coordinate for that y-intercept. Domain and range. So the domain is -∞ to infinity, same as it was for the parent function. The range, that's going to change. So our range would have been -1 to 1. The reflection isn't going to change that because this 1 is going to turn into a -1 and this -1 is going to turn into a +1. So reflection doesn't change the range, but the vertical shrink does. So it's going to be -1/2 to +1/2. And then the horizontal shrink won't affect it. That would affect x, but since it's infinity, half of infinity, or actually a fourth of infinity, is still infinity, so it's not going to change it. So the only effect on these two is going to be the range is now going to be from -1/2 to 1/2. All right, so the directions up here ask me to answer all of these questions and also to verify the results with a graphing utility. I didn't do the first one. Let's just go ahead and do the second one only here and just take a look at what this graph looks like. We already did a sine function on the previous page. So let's do a cosine function. And one transformation at a time. Oops, cosine. All right. So I just need to get this scaled up. So I want my y-axis just to show from -1 to 1. And my x-axis, let's go from -2 pi to 2 pi. And I want my steps here to be pi halves. All right. So looks pretty good for this graph. I can zoom out once I get it all nice and scaled there. Okay, so one thing at a time. Let's take care of our reflection. So our reflection, we're going to multiply by a negative. There we go, a negative. So definitely reflected. So that negative does do the reflect effect. And then we're going to do the 1/2. And the 1/2 we said was going to be a vertical shrink. So the blue graph is vertically shrunk by a factor of a half. Perfect. And then from there, we're going to horizontally shrink this by a factor of 4. That's going to smush it up so that the graph gets thinner, horizontally shrunk. So there we go. That blue graph's now squished in there a lot thinner by a factor of 4. So if this value is at pi halves, this one should be at pi eighths, right? 1/4 of pi halves. All right. So I can compare this to the original graph of cosine and look at the full set of transformations have been reflected, vertically shrunk, and horizontally shrunk. Okay. Also, just to confirm, domain sure is all real numbers, and the top and bottoms are at -1/2 and +1/2. So if we were to adjust this step scale and make it by, let's just do 1/4, see if that works. There we go. So we can see that 1/2 is the top of the range and -1/2 is the bottom of the range, as we were suggesting. Okay. Y-intercept also we said was going to be at 0, -1/2, matches up with our graph here as well. So we're able to confirm all of our work here on the graph. All right. Let's go on to the next page. Okay, we've got tangent, cotangent, cosecant, and secant. So let's get all of our transformations, and we'll pick 1 or 2 of these to graph. So this one printed a little funky, but the base function here is going to be tangent of x. Looks like the box was a little too small. It couldn't all fit on one line, but we have a couple transformations. So the first transformation, this negative, is going to be a reflection across the x-axis. Then inside the tangent function, we have a 1/2 multiplier. So that 1/2 multiplier is going to be a horizontal stretch or shrink. And in this case, since it's a 1/2, it's going to be a horizontal stretch by a factor of 2. And then the -2 at the end, it's not inside the parentheses. It's not inside the tangent function. That's going to be a shift down 2. All right, so this is supposed to be in this box here where we put the y-intercept, and this is supposed to be our domain and range. For tangent, since we don't have the parent function memorized, we're going to make sure we look back at our parent function graphs from the previous page. So tangent did have 0, 0 as its original y-intercept. If I reflect 0, 0, it stays at 0, 0. If I shrink 0, 0, 0 divided by 2 is still 0. But if I shift it down 2, that is going to change its position to 0, -2. So the new y-intercept will be at 0, -2 from moving down 2. All right, so think about our domain and our range. For tangent, the range is going to be the easier one for us because it's -infinity to infinity. When you transform that, it just stays as -infinity to infinity. But we're going to have to work a little harder for the domain with our transformations. Domain is only affected by the x value, so the reflection and the horizontal stretch are not going, the reflection and the shift down are not going to change the domain. The horizontal stretch factor is going to change the domain because this one affects x. So each of these needs to become twice as large. So if I imagine multiplying this by 2, making them twice as large for that stretch factor, that 2 would reduce with the pi halves, and we're going to have odd multiples of pi. So x is not equal to 2k plus 1 pi. So I multiply this by 2, right? Because I'm horizontally stretching by a factor of 2. All right, let's just go ahead and see how we did on this one. So our parent function is going to be tangent. Let's turn that one on. And we'll do one transformation at a time. I'm going to zoom out on that a little bit. All right, and I just want to rescale. I don't need 1/4 as my step anymore, so let's make it 1. Okay, so the first transformation is the reflection. It's been reflected, so that looks great. So we know the reflection was the correct transformation there. The next transformation we said horizontally stretched by a factor of 2. So we're going to get wider down the x-axis when we put in this half here. Let's see how that stretch looks. So we were able to pull each of the red points over by a multiplier of 2. And I should draw in the asymptotes as well. Let me just draw in one of the asymptotes for the original. It would have been at x equals pi halves. And so I'm going to dot that for an asymptote. That is an asymptote to the original red function. Twice that, x equals pi, is now an asymptote for the graph of the blue function, right? So we got twice as wide there for our asymptotes as well. If you zoom out, you can really see us getting close to those asymptotes. The original function has asymptotes at pi halves. The new function doesn't have an asymptote until pi 2 times as big, as we were saying over here, all those multiples of pi. And then we're going to shift down 2. So let's put in our half here. Oops, I need to put parentheses. And the transformation is going to shift this function down 2. So that did move the y-intercept down to -2, and the up-down shift did not affect the location of the asymptote. Okay, so that is the finished graph. It does match all of the things that we were saying in the boxes above. Okay, let's talk about the cotan function. Cotangent of x plus pi plus 1, the base function, is f of x equals cotangent of x. Just 2 transformations here. We've got ourselves a plus pi happening inside with x. So that's going to be a left or right shift. In this case, that's going to be left by pi, or shift left by pi units. And then outside of the function, we've got this plus 1. So that's going to be up or down. So that's going to be shifting up by 1. All right, back over to our parent function. Notice that on cotangent, our parent function did not have a y-intercept. However, if we take a point and shift it to the left by pi, this is where pi is. So whatever's at pi is going to shift to the left and become at this intercept. So it looks like since pi happened to be another asymptote, we're still going to have an asymptote on the y-axis. So there's not going to be a y-intercept. And if I shift up 1, that's not going to change the location of any point because there is no point right here. So we're going to say that there are none in terms of the y-intercept because of these transformations. Okay, so domain and range. The domain for cotangent, we'll have to work on that with the transformations, but the range is going to be -infinity to infinity, as it always is. So we'll write that one in first. Without transformations, it was all multiples of pi. This is x values for the domain. So if I shift this to the left by pi, I'm going to be taking all multiples of pi, and they're going to stay on all multiples of pi. So it's actually not going to change the domain. It's going to shift right on over. So x is not equal to k pi or n pi, whatever letter you like. Oops, not kn, k pi. There we go, k pi. All right. So this graph is actually going to look very similar. If you do graph it and check, very, very similar to the parent function because I'm shifting a whole period. Pi is the period, right? Shifting over a whole period, it's going to look identical. Only thing you're going to see is the up 1 shift. All right, let's not graph this one. I'm going to go ahead and do the next 2, and we'll graph one of those 2. So on the next one, I have a 3 multiplier. I should write the base function first here. The base function is cosecant of x. And that 3 multiplier is going to be a vertical stretch by a factor of 3. Then I have this 2 that's inside with x, so that's going to be, it's a horizontal stretch or shrink factor. Vertical stretch when they're bigger than 1, horizontal shrink when they're bigger than 1. This is going to be a horizontal shrink by a factor of 2. And then we are going to have a left or right shift. Unfortunately, I do not yet know what my left or right shift is. It's going to have to do with this portion. However, that 2 affects it as well. So I'm going to rewrite this with the 2 factored out. This is 3 times cosecant of 2 times the quantity x plus, I'm going to divide that 2 out, so it'd be x plus pi halves. So I need to divide out the horizontal shrink multiplier to figure out what is the value of the left or right shift. So the value of the left or right shift is actually by pi halves. It's positive. So this is going to be a shift to the left by pi halves. Okay. Let's take a look at our parent function for cosecant. The cosecant parent function does not have a y-intercept, but we've got some transformations to do. We're going to horizontally shrink this by a factor of 2, which would definitely affect the values here. And we're going to shift it to the left by pi halves. So there's a good chance that we will have a intercept when we're done. And then the vertical stretch factor might change its location as well. So let's take a look at this one on Desmos, since it's not one of the 2 that we need to have parent functions memorized for. Let's do cosecant of x as our parent function. I think the parent function I typically call f. And we're going to work on g of x with our transformations. All right, I want to work from the inside out. So first, let's do our horizontal shrink by a factor of 2, putting our multiplier of 2 inside. So what I notice about this, the purple graph, it is half as wide as the original blue. It did get shrunk. It does still not have a y-intercept, but we are going to give it the left shift by pi halves. So pi halves is here. Pi halves is an asymptote. So when I left shift by pi halves, I can actually just add pi right here to left shift by pi halves. This moved over by pi halves, and because it moved over by exactly pi halves, the asymptote that was here at pi halves has moved over to 0. So it looks like we're not going to get a y-intercept from this function as well. And then the last thing doesn't going to affect it. The last thing is a vertical multiplier. It's just going to make this guy taller. So now it's taller. So it looks like there is going to be no y-intercept, based on the fact that these numbers, pi halves, and the shrink factor of 2, kept the asymptotes, kept an asymptote here at 0. Okay. All right, so there we go. There's our original function, and there is our function that's been shrunk horizontally, shifted left, and then stretched. So in terms of the domain, that did change. So let's look at the domain of the original again. The domain of the original was all things that are not multiples of pi. So I'm going to write that outside. X is not a multiple of pi. But when I horizontally shrunk this by a factor of 2, that would have turned out to x is not equal to k pi over 2. Then when I shift this left by pi over 2, since this is all multiples of pi over 2, if I add in another pi over 2 or subtract another pi over 2, it's not going to change these. So it should be all multiples of pi over 2. So x is not equal to all multiples of pi over 2. Let's just check this. If I look at x equals 1 pi over 2, I'm going to turn off the original function here. Or if I look at x is equal to 2 pi over 2, that's pi. That's another asymptote, right? So I've got asymptotes at pi over 2, 2 pi over 2. This one would be 3 pi over 2. That one's 4 pi over 2 or 2 pi. Looks like we're definitely on the right track with that multiples of pi over 2 for our domain. For the range, the parent function's range would have been all things that are less than -1 or greater than 1, but we have vertically stretched this by a factor of 3. So I would expect that these are all things below -3 as the output value, and all things that are above +3 as the output value. So the range is going to be from -infinity to -3 due to that vertical stretch factor, and then from 3 to infinity. Okay. The last one here has a parent function of secant of x, and there are several transformations. The first transformation, that multiplier of 3/2, is going to be a vertical stretch or shrink. Remember, we stretch if it's bigger than 1, and we shrink if that number is less than 1. 3/2 is larger than 1. It's 1.5 in decimal form. So this is going to be a vertical stretch by a factor of 3/2. Then I'm going to need to reorder this function to talk about the other transformations. So this is y equals 3/2 secant of. In the inside here, 3 pi minus 2x, that's backwards. We should write the x first. So if you think about that as -2x, let's also go ahead and factor out the -2. This would have been -2x. Let me just write this down here below. -2x plus 3 pi, and I'm factoring out the -2. So when I divide by the -2, that's going to make this -3 pi over 2. If I multiply by -2, I get back to +3 pi. So I want -2 times the quantity, x minus 3 pi over 2. And then close the first parenthesis for secant. So there's a lot going on. We've got our 3/2 is our vertical stretch. The negative on this -2 is a reflection across the y-axis. That's the x reflection. So we're going across the y-axis. Most of our reflections from negative coefficients are across the x x-axis. This one on the inside is a reflection across the y-axis. Then we have the 2 itself. So the 2 is going to be a horizontal stretch shrink. It's bigger than 1, so that means horizontal shrink. So horizontal shrink by a factor of 2. And the last piece here, this minus 3/2 on the inside is going to be a shift to this would be inside, so left, right. We got minus, that's going to be to the right by a measure of 3/2. All right, so we're going to find the y-intercept and then our domain and range. Once again, we're going to graph this just to get us some help with where those items are going to go. So I'm going to clear this. Actually, I don't want to clear it because I want to keep my scaling. Let me just close these. So parent function is secant of x. And with our transformations, again, we can do these in any order. I'm going to work from the inside out, just doing the vertical stretch last because it's the least involved of my transformations. So let's do first our reflection. This is a reflection across the y-axis. So nothing appears to happen. And that's fine. It's because points on the left side reflected over to points on the right side. This was already symmetric across the y-axis, so I don't see a change when I apply that reflection. Okay. Now, we're going to do the horizontal shrink by a factor of 2. We should notice a change here. Horizontal shrink, so the green function became smaller by half than the blue function, and 2 of them appear where previously 1 of the blue ones appeared. So horizontal shrink, we can see that happening here. Okay, so horizontal shrink is changing where the asymptotes are. So let's talk about our domain here. The domain would have originally been on the secant function, odd multiples of pi halves. X is not equal to the 2k plus 1 pi halves. And if we shrink by 2, this is now going to be x is not equal to, if I divide this by 2, it's odd multiples of pi fourths, right? So 2k plus 1 pi fourths. And if we expand our scale here, we should hopefully be able to see on the green function, I think that would be pi fourths, right? Let me just get the scaling up here to step this by pi fourths. Yep, on our green function, pi fourths and 3 pi fourths, the odd multiples of pi fourths are going to be where our asymptotes are. So that looks good. So let's implement that change, and we'll go on to the next change. The next change is going to have the shift to the right by 3 pi halves. So 3 pi halves is right here. This is going to move to the right. So I should actually go ahead and figure out where negative 3 pi halves is. Right here. This is going to move to the right. And so this point right here, I'm going to expect to land on 0. So I'm going to watch this point here move on to 0. I'm going to write this in the original format just so that I can verify I haven't made any mistakes when I've done my factoring. So I'm going to type in the 3 pi in the front here. And we're going to watch that point right here that was blue moved over here. So this point moved over to here in the green graph. I do have a point right there where I was expecting. Okay, now that is going to, it's going to, let me think what I'm going to say here. It's going to change the location of the y-intercept because it previously on the blue graph was up here, but as I move this over, of course, now it's down here. It does not look like that shift to the right affected the domain. And the reason for that is because 3 pi halves is, let's see, an even multiple of pi fourths. So if I take 3 pi halves, that would be 6 pi fourths. If I take an odd multiple of pi halves and I add an even number to it, an even number plus an odd number is always an odd number, which is why I stated the odd multiples of pi fourths. Okay, so we've done the reflection across x, the horizontal shrink, and the shift to the right. Those are the only things that affect the x coordinate. So we're now done with our domain. It's going to be x is not equal to odd 2k plus 1 multiples of pi fourths. I still need range. So range has not been completed yet. Range on these right now are negative infinity up to -1 and -1 up to infinity, but we need to vertical stretch by a factor of 3 halves. So let's put in our shift here and take a look at what that 3 halves is going to do. It's going to stretch it just a little bit. So now we are down at -3 halves and up at +3 halves. So this is going to go from negative infinity up to -3 halves, and then we'll continue from +3 halves up to infinity. And the location of the y-intercept, there is one. The y-intercept formerly was at 0, -1 until we did the vertical stretch. So now it is at 0, -3 halves, or -1.5. That's just the fractional form of, I'm going to use the fractional form because it was given that way in my question. Okay, so we have all of our transformations, and if we look at them one at a time, we can see their effects on the domain, the range, and the location of the y-intercept. Okay, so in general, we can make use of our knowledge of function transformations to create practically any kind of trigonometric function graph. And with a little time, some curiosity, and decimals, we can work on these somewhat easily. So there's some trig transformations of graph. If you want to play with them, you can use that bit.ly link and do some exploration. On the next page, in general, if we're looking at y equals a times any of our trig functions, sine, cosine, tangent, cosecant, secant, cotangent, of bx minus c plus d, the transformations are going to be the same, and we have our trig functions interchangeable here. We know that the value of a, that's going to be a vertical stretch. Let me just write that in. That's going to be a vertical stretch. Or shrink, right? Depending on how large the value is. And so the absolute value takes away the negative. So of course there could be a reflection as well here. But reflection is not going to change the amplitude. So the amount by which you are vertically stretched or shrunk is going to affect the amplitude of the graph. Now, amplitude does only apply to sine and cosine because those are closed curves. Amplitude does not apply to the other four. Remember, amplitude is the distance to the top and the bottom from the x-axis. Sine and cosine have amplitudes. These other guys don't have amplitudes because they go up infinitely high and infinitely low. So the only two that we can apply the word amplitude to are sine and cosine. Otherwise, when it's not sine and cosine, we do, of course, think of this as the vertical stretch, as we were saying up here. A is the vertical stretch. Amplitude is the special case word that we can use for vertical stretch in the terms of sine and cosine. All right, other values. So D, this value on the end, is the vertical translation. So my upshift or my downshift, depending on if it's bigger than 0 or less than 0. The phase shift, so for a phase shift, that's going to be a shift left or a shift right, is, remember we need to factor B out. So this is B times the quantity x minus c over b. B is the horizontal stretch shrink factor, and the phase shift part of it is this value c over b, right? So it's the quantity c over b, and the minus is part of our formula right here. So if we see something that has b times x minus c over b, just like this is going to be to the right by c over b units if we've got x minus c over b. But if we have b times x plus c over b, then that's going to be our shift to the left by c over b units, right, with the addition. So they're saying if this is less than 0, meaning two negatives make a positive on the inside, right here, we go to the left. Okay, so phase shift is our shift that's in the left or right direction. So it's got its own special name. And of course, there's other transformations. Like we know that B itself is the horizontal stretch or shrink. It doesn't get a special name. So we're only writing down things that have special names like amplitude, phase shift, vertical translation. So we know that B is the horizontal stretch shrink. And not even mentioning all of the possible reflections if A or B is negative. So of course, those are regular transformations. Continuing, we're going to look at how the period of a function changes. So the period is the distance between repetitive patterns. And so if you're looking at the sine, cosine, cosecant, or secant graph, the period of those functions would have been 2 pi in the parent function. But if you have a horizontal stretch or a shrink by that factor of b, you need to divide by b. So you need to divide by b, and it does say absolute value because, of course, the negative, if b is negative, is just going to be about reflection, not about changing to the period. So you divide by the absolute value of b. Okay. If it is a tangent or a cotangent graph, then you just divide pi by b because the period of the parent function, tangent or cotangent, is pi, not 2 pi, like it is for the other 4. Okay. And the last item in this chart is the frequency, another special word for trigonometric functions. The frequency is telling us how often the repetitive pattern occurs. That's actually just the reciprocal of the period. The period is how long it takes for the pattern to occur. So its reciprocal is how often the pattern occurs. So for sine, cosine, cosecant, and secant, you're going to take b and you're going to divide it by 2 pi, reciprocal of the period. And then for tangent and cotangent, you just divide by pi instead of 2 pi because, again, that is the period of the parent function. Okay, so let's take a look at a few more examples here. We're looking at this function. It's a cosine transformation, And we're going to use what we know about transformations to predict the amplitude, period, x-intercepts, and y-intercepts of the graph. And we have a sketch right here of the parent function. I would like to first write down all of my transformations and then relate those to these phrasings specific to the trig functions. So the first transformation from this negative is going to be a reflection across the x-axis, outside reflection, so it's a y-valued reflection. Then this 2 is going to be a vertical stretch by a factor of 2. Then this 2 is going to be a horizontal shrink. So number bigger than 1 on the inside, so it's a horizontal shrink by a factor of 2. And then the left-right shift, I'm not able to see without factoring. So let's get our 2 factored out. 2 times x minus pi over 2. When I factor, I divide out that 2. So that's going to be a shift to the right by pi over 2. And then this plus 1 is going to be a shift up 1. It's a lot of transformations. We got 5 transformations to this graph. I'm going to use these transformations to predict the amplitude, period, x-intercepts and y-intercepts of this graph. So first of all, let's go ahead for amplitude. Okay, so amplitude is based off of the vertical stretch factor. So the vertical stretch is a factor of 2, so the amplitude is 2. Period. The period of the parent function is 2 pi, so I need to take 2 pi divided by b, where b is the horizontal stretch or shrink factor. In this case, it was a shrink by a factor of 2. So 2 pi divided by 2 is going to be pi for the period. And then I'm asked about the x-intercepts and the y-intercepts. I'm going to get to those, but let's talk about some of the other terms right here as well. So let's talk about, we talked about amplitude and period. I'm not entirely sure why this question skipped the other things, but we'll do the vertical translation, the phase shift, and the frequency as well. With period, let's just do frequency next, because it is the reciprocal of the period. So if the period is pi, the frequency is going to be 1 over pi. To get our phase shift, I'm just going to back up the list now. The phase shift is the amount shifted to the left or the right. So the phase shift is going to be pi halves, and that was a shift to the right. So it's positive because I went to the right. If it had been a shift to the left, I would have said negative pi halves, and the fact that it was to the left. And then the vertical translation. That's an up 1 from our shift up 1. All right, so the location of the x and y intercepts, there's not a quick formula for how to find those, so we're going to just consider where they might be. So the cosine function has an x-intercept at pi halves. If I increase the amplitude to 2, that's not going to change an x-intercept, that's going to change a y-intercept, so we'll get to that in a minute. And then if I shrink the period down to 2 pi, with that horizontal shrink factor, that's going to move it over to a quarter of pi. That's going to move it over to pi fourths. And this one's going to move down to 3 pi fourths and so on. So 3 pi halves moves down to 3 pi fourths. And then we phase shift these by pi halves to the right. So pi fourths, 3 pi fourths. If we phase shift these by pi halves, where are they going to move? So pi halves is 2 pi fourths. So this would be an even amount of pi fourths. And right now they are at odd multiples of pi fourths. So if you take an odd multiple of pi fourths and you add an even multiple of pi fourths to it, odd plus even is still odd. So we're going to stay at odd multiples of pi fourths. So the x-intercepts are going to be at odd multiples of pi fourths. So that's our 2k plus 1 pi fourths, comma 0 for x-intercepts. All right, the y-intercept, that used to be at 0, 1. I had to shift everything, we had to shrink everything by a horizontal factor of 2, which would have left it where it was because the x-coordinate is 0. Divided by 2 is still 0. But when I shift this to the right by pi halves, where does that end up? So we've drawn in the new x-intercepts for the shrink here. That's pi halves. So if I shift to the right, oh, that was left. So sorry, we're shifting this way. If I shift to the right by pi halves, this guy is going to be moving over to the y-axis. So this point right here would be my new y-intercept. So at the moment, I'm at a 0, negative 1 after the horizontal shrink and the shift to the right. Then I need to take that point, I need to reflect it up, stretch it up to 2, and then I need to add 1 to it. So I should be ending at 0, 3 for my y-intercept. What I would say about these is that we should absolutely be able to determine the amplitude, the period, the frequency, the phase shift, and the vertical translation from just the A, B, and C values. These other values over here for the x-intercepts and the y-intercept, it's absolutely fine if you use the graph to help you. I'm trying to illustrate how I can find them. But it's okay to use the graph to find those. Let's take a look at the graph and confirm that we've done a good job. All right, so I've got myself a fresh graph. It's in radian mode. And let's look at the parent function, which was cosine of x. Let me get this rescaled. Step on 1, step by, I'm going to make this pi fourths. And I want to look at this from negative 2 pi to 2 pi. Just zoom in a little bit there. Okay. Parent function. And the graph I want to do, one transformation at a time, we're going to work from the inside out. So we're going to start with the 2, which is the horizontal shrink. So the blue graph is horizontally shrunk. It now intersects, like we said, at pi fourths and 3 pi fourths and so on. That's done the job we were hoping. Then we're going to subtract our pi, which was supposed to move this over by pi halves. So again, we were saying that this point right here, negative pi halves, if you add pi halves to it, that puts you at 0. It's going to move to right here. So let's watch that happen when we do the minus pi. So again, this point right here has moved over here. Looks good. So we have the correct assumption from our negative pi transformation. All right, so that is the inner two pieces. We're going to take a look at the reflection and the multiplier by 2. That's going to, like we said, flip that point that used to be down here at negative 1 up to a positive 2. And then at the end of this function, we're going to add 1. And so we end up with a height at 3. So checking all of our details here, the y-intercept is at 0, 3. Oh, I forgot about the plus 1 when we did the x-intercepts. Ooh, that's going to be making these incorrect. So hold on just a second. We were all good with these x-intercepts right here at odd multiples of pi fourths, but we forgot that plus 1 is going to shift those. So this right here needs to change. This is without the up 1. So we're going to have to change this, and it's not going to make them pretty. So let's put in our negative 2 right here. When I add that 1, they are now at, it looks like pi thirds and 2 pi thirds. Let's see if we can figure out why. So before we added the 1, we're looking for the values. So if I'm going to shift this up 1, I need the values that are at negative 1 here and here. I would need to solve for what value was going to make this function equal to negative 1. So it turns out that it happens to be pi thirds and 2 pi thirds, negative pi thirds. It looks like multiples of pi thirds and 2 pi thirds. It's just not going to have the pi multiples. I meant like 3 pi thirds, which is pi. So I've got 1 pi third, 2 pi third, 3 pi third is not an x-intercept, but 4 pi third, 5 pi third is. So it's all of the ones that don't reduce. So again, we should be using the graph for these. We did a really good job. We got all the transformations. I just forgot about the up 1. So our actual x-intercepts, let me write up here. They are going to be at, now I have a hard time with this pattern because it's not all odds and it's not all evens. The odds that we don't include are any multiple of pi, and we don't include any multiple of 2 pi. Let me clear off the red one here. So I want 1 pi third, 2 pi third, 4, 5, and 7. So we're skipping 3 and we're skipping 6. So I need to keep, I could make a pattern for this, or I'm just going to list them. I think that's going to be easier right here. So we want pi thirds, 0. I'll get to the pattern. 2 pi thirds, 0, not 3 pi thirds. 4 pi thirds, 0. 5 pi thirds, 0, not 6 pi thirds. 7 pi thirds, 0, etc. Okay. It's going to be kind of complicated to make a pattern for this. We're not going to do that right here. The pattern building for this kind of expression where I'm doing all multiples that are not even or not divide out evenly is something that you practice in Calc 2. So I'm going to leave that to future us to figure out the pattern for those. It would deal with sequences and series, which is a topic discussed and discovered in Calc 2. So we're just going to list these, a few of them, And unfortunately, the reason that this one didn't work out the way I was originally hoping was that up one. That up one just messed those x-intercepts up because it did shift them, of course. All right, back to our things that we got right. All of the things that we can tell from the graph is we can tell that the amplitude is 2. I'm going to draw in the y equals 1 line right here. That's from the up 1 shift. And so from the up 1 shift, which is the baseline for this graph, you can see that we've moved up a distance of 2 and down a distance of 2. That's the amplitude. We can also see the period here is we're repeating in the span of a single pi. And the frequency is just the flip of that, so 1 over pi. The phase shift, pi over 2 from the right, we verify that as we are graphing it out, and we do, of course, have the up 1 shift that we verified as we were graphing it out. Okay. All right. Aside from a little more space needed, we did a pretty good job on this one. And the last page, or the next page, just has a summary of trigonometric transformations, what we need to do in order to graph a transformed trigonometric function. We first need to recognize the base trigonometric function, whether it's sine, cosine, cotangent, tangent, etc., and sketch a graph of that parent function, including a few periods that you're able to look at the key features, the x-intercepts, y-intercepts, max, min, and any asymptotes. Once you've taken a look at the base or parent function, make sure that you rearrange your function into the general form so that you can identify your a, b, your c over b, and your d values for your function, whether it's a sine, cosine, tangent, or whatever, because you're going to need those values. That might involve reordering or factoring in order to identify those values. Okay, next, we are going to stretch, shrink, or flip according to B. So we work from the inside out. So we're going to do our horizontal stretches if that B value is small. We're going to do our horizontal shrinks if that B value is larger than 1. And we're going to reflect across the y-axis if that B value is negative. So we work from the inside out. We'll work on our B. Now, the order of the next couple of steps is up to you. You can do your stretches and vertical stretches and shrinks next. I tend to continue on the inside, so I would do my shifts, translate the graph according to the C over B, and that's going to be to the left or to the right, depending on how big that value is. And so that value is defined as the phase shift. So we know we're going to the left if we've got ourselves an x plus c over b, and we're going to the right if we've got ourselves an x minus c over b inside those parentheses. So I would do my phase shift next. And then I would come back and do my A, which is my vertical stretch, shrink, or flip. So this is the vertical stretch according to A. We know that B was the horizontal stretch, shrink. And if you've got a small a, you're going to shrink vertically. If you've got a big A, you're going to stretch vertically. If it's less than 0, you're going to reflect across X. And then if it's a sine or cosine function, you can use the A value for the amplitude. The tangent, cotangent, cosecant, and secant functions don't have amplitude. They would just, again, have a stretch or shrink factor. All right, so if we went inside out, we did our horizontal stretch shrink, our horizontal shift. Now we've done our vertical stretch shrink, reflect. And last, we have our shift up or down. And so that's just going to be our shift down for the little values and our shift up for the big values. We've got one more here. Unfortunately, we don't need the x and y intercepts on this one. As we noticed, those were a bit more challenging in that last one. We just want to identify the amplitude, period, and phase shifts from our transformations. The first transformation is I've got a vertical stretch. Vertical stretch by a factor of 2. I've got a horizontal shrink. Let's get that 1/2 factored out here. 1/2 times x minus pi. Can factor or divide half out of both of those. So half is going to be horizontal stretch or shrink. It's less than 1, so that's horizontal stretch. Horizontal stretch, because it's a small number, by a factor of 2. Then that minus pi is going to be a shift to the right by pi units. And then the plus 1 is going to be a shift up 1. Again, I'm shifting up 1, so that's going to certainly mess with x and y intercepts, so I'm glad I'm not writing those down. Okay, so amplitude. It is a sine or cosine function. It's a cosine function, so it has amplitude. Tangent would not have an amplitude. You would have said none. Or cosecant, secant, all those other ones. Cosine has an amplitude, and it's based on the a value, so the amplitude is 2. Any period. The cosine function has a period of 2 pi for the parent function. We're going to divide that by 1/2. So that's going to flip up and make this 4 pi. Horizontally stretched, so wider, longer period. And then phase shift. Is to the right by pi. And we're asked to verify this, so we'll do another graph right here verifying these transformations and shifts. So my parent function is y equals the cosine of x. Our new function, from the inside out, we're going to have a horizontal stretch by a factor of 2. Let's watch this get wider. Okay, very much wider here. I'm going to have to shrink down on this axis. Okay, wider. Now we're going to take it and shift it to the right by a unit of pi. So this is pi. It's going to move over here by a pi. So 0 is going to move over to pi. I'm going to have my maximum at pi when I do the minus pi over 2. Okay, moved over to the right by pi. Looks perfect. The multiplier is going to stretch, make it taller by a factor of 2. Looks good. And then finally, the up 1 shift is going to mess up all our intercepts and just push this up by a factor of 1. And they're at these weird numbers again because of the vertical shift. Okay, if I wanted to verify the amplitude, I'm going to graph y equals 1 again. Oops, that was supposed to be a 1. And I can see that I am from 1 to 3 is a distance of 2. From 1 to negative 1 is a distance of 2. So that's up 2, down 2 for the amplitude. The period is 4 pi. It takes me until a distance of 4 pi to begin the next cycle of the repetition. And as we said before, the phase shift was by pi to the right. We confirmed that as we were working through our graph. Example 5 says that after conducting an exhaustive study on the pathology of certain diseases, the doctor finds the body temperature of a patient, B, in degrees Fahrenheit follows a particular periodic pattern over the course of time, T's in days, when they are symptomatic, typically about 3 days. based solely on what I know about transformations of the basic sine function, what does the model predict for the patient's high and low body temperatures? Based on what I know about transformations, I can see that I've got this amplitude of 3 and this vertical shift of 101.6. So the patient's high and low is going to come from this 101.6 plus and minus 3 degrees, because that's our amplitude, the amount we go up and down from base. So for high, we would have a high of 104.6 degrees, and low, I'm going to use a calculator to subtract till I get my numbers right here. We've got our 101.6 minus 3. That's going to be a low of 98.6 degrees. How much time is there between spikes in a patient's body temperature? So the time in between spikes, if we think about where a spike is, that's going to be a single period, right? The time in between two spikes, that's where the pattern begins to repeat. That's going to be 1 period. And I can figure out just based on this function, I don't need to see its graph, I can figure out just based on the values in the equation what the period is. So I can see that the B value is pi eighths, and I know that the period is going to be 2 pi, since it's a sine function, sine and cosine, and secant and cosecant have a base period of 2 pi, tangent and cotangent would be pi, divided by the B value of pi eighths. So that's going to be 2 pi times 8 over pi, if I change the division into multiplication by the reciprocal. And pi would cancel, and this would be 16. So it would be 16 days in between spikes. We can graph this to confirm. We'll go ahead and do that here. Let me just clear this. We have B of t, it's supposed to be a B. B of t equals 101.6 plus 3 sine of pi over 8t. I need to rescale this because I know that the maximum high temperature here is going to be 104.6. Let me just make this 110. And I know that a period is 16 days. Let me make this 32 so I can see 2 periods. Okay, maximum temp, 104.6. Minimum temp, 98.6. And a period from one repetition to the next should be about 16 days. Since this has a weird value of 1.106, I could graph, that is my vertical shift there, y equals 101.6, and I can see that when I'm on the way up towards that, it takes 16 days to be on the way up past it again. So the period is 16 days. Okay. So typically, the patient will only follow this pattern, they said, for 3 days before medication or whatever takes hold. So if I were to shrink this down and look at it between 0 and 3, this would be the picture of the patient's temperature. So slow, up, and then hopefully at that point is when they're going to start getting some medical treatment. Okay. All right. Just an example here of what we can learn just by looking at the function about the behavior of this graph. All right, long section here, but we're on to our last example. At the beginning, we said that we're also going to look at graphs of sums, and this is going to be a small thing, but one of the more interesting and useful applications of periodic functions is the way we can combine them. We can add or subtract them to make more interesting and complex periodic functions. We can use this to model many phenomena from digital musical files to earthquakes. So, in example 6, sometimes two tones played on top of each other can overlap in some interesting ways. We can model these effects with superimposed trigonometric functions. We are first going to graph f of x equals sine x, set it up so I can see two periods, and then we're going to graph g of x equals sine of 2x on the same graph. So let's get that part started before we continue. So I'm going to reset this, and f of x is going to be sine of x. I missed the equal sign. And g of x is going to be sine of 2x. Let's rescale this so that I only see wrong button there. Between -2 and 2, step size of 1 on the y-axis, and I want to see two periods. I'm going to go from negative 2 pi. I'm going to see 3 periods. I'm going to go ahead and go to 4 pi so I can see two periods in the positive side right here. So one at a time right here. There's the sine of x graph. I really do need to rescale this by pi halves, so it's just in terms of pi on the x-axis. 0 to 2 pi, that's one period. 2 pi to 4 pi, that's my second period. And the 2 pi x, that one has been shrunk down. Let me make that bigger. It's been shrunk down with a horizontal shrink, meaning that its period is 1 pi. So I can see 1 pi period, I can see 2 periods, I can see 3 periods, and I can see 4 periods. All right, so we've graphed them on the same graph. Then our question is, what do you notice about where they touch? Is it at a maxima point or is it somewhere else? So it's somewhere else, right? They're touching somewhere else. They're not touching at their maximum. So they're touching at pi thirds, and again at 5 pi thirds, and again at 7 pi thirds. I guess I missed some of these zeros. So they're touching at pi and 2 pi and a bunch of weird places. Okay, so they're touching elsewhere. What do you notice about where the functions are both positive or negative? Okay, so they're both positive when the 2x function is positive for the first cycle. Then we have to wait until the second cycle of the blue function. So we've got the first period. In the second period, this one's negative. In the third period, they're both positive. So it's every other period in the blue function. Okay, so they're both positive in every other period of the sine of 2x function. Just observing that. The where I touch, I could have written down values, but we were just kind of observing they were elsewhere from what we were asked. They happened to be at x equals pi thirds, and then pi, and then 5 pi thirds, if we wanted to write down a few of them, and then 2 pi, and then etc. But elsewhere speaks to their heights. Next, add to these graphs a third graph, h of x equals 2 sine of x. So that should match the red graph, but be twice as tall. Do I see any points that are common amongst all three? Now it is only the x-intercepts that all three have in common. Okay, so we have some x-intercepts in common. So we've got x equals 0 and pi and 2 pi and so on. And those are the x-intercepts for the original function. They're every other x-intercept for the horizontally shrunk function, and they match the x-intercepts for the vertically stretched function. Now try unselecting the previous function graphs and graph the following function, g of x equals x plus h. So I'm just going to graph that and then unselect. So g of x plus h of x. Okay, so let's turn off these. And this is a graph of the sum. Let's zoom this out a little bit. So when I add these two functions together, the g of x function and the h of x function, their x-intercepts are going to stay in the same place because when I add the y value of 0, 0 plus 0 is still 0. So I still have x-intercepts at 0 and at pi and at 2 pi and pi. But the graph takes on a really cool shape. So remember, I'm adding up these two, and you can kind of see why the wiggle looks the way it does. You're going to take these height values, and here I'm adding two positive heights together. At this point right here, I start adding a larger positive height to a smaller positive height, and then here I'm adding 0, and then I start adding a lower value to a negative value. So that's what's causing these interesting curves to this shape right here. And there are bumps in the pi region, not in the 2 pi region, bumps in the 3 pi region. And again, that's because this function is flipping on a period of pi, not on a period of 2 pi. So the full period of this larger function is 2 pi based on this guy's period and has those little bumps and flips based on this guy's period. So, conclusions. What do you know about the period, the amplitude, and the general shape of this new function that is the sum of the others? Okay, so its amplitude is probably, let's see, this some weird number. Why it's this weird number is because at the peak, I'm adding 0, but at that weird number, I'm adding the combination of a relatively high value to a not quite small value. It just comes out as the high value up here. I don't know what it is in terms of an exact number. But what I would need to do is figure out the pi thirds coordinates of each of those if I wanted the exact value. Okay, but the amplitude is something along the lines of 2.598. I'm sure that if I wanted that expressed as an exact number, I could evaluate these functions at pi thirds, and it's going to have that square root of 3 over 2 in it somewhere for pi thirds. Okay, but added the two function values together. The period, we did say, was going to be 2 pi. And then the general shape is very different from the originals because of this wiggle thing through every odd multiple of pi. So I'll just make a note about this. We have these wiggles, I'm not sure what else to call them, at odd multiples of pi. The differences in shape that we see for different trigonometric functions added together or subtracted is a way of mathematically modeling what we hear sometimes when we listen to things like tone or tenor or timbre of musical notes when they are played together. All right, so that's an end of this section. We'll see you back for the next one.